Hi guys, welcome to lecture 3 on chapter 13. We're going to talk about implementing a stack using links. So our linked stack class stores a generic type T and implements the same stack ADT that we used previously. So we're going to implement the same interface that we used when we did the array implementation, but we're going to use a linked stack class instead. Or we're going to use a linked list instead, sorry. So there's a separate linear node T class that forms the list and holds a reference to the element stored, and we have an integer count that will store how many elements are currently in the stack. All right. So since all the activity on the stack happens at one end, a single reference to the front of the list will be used to represent the top of the stack. So again, we talked about different types of linked lists that we could implement. In this case, because we're basically just going to pull and push. That's why I said linked lists are so great for stacks, because we only pull off the top. We pull and push off the top, so we really only need a reference to the top, so we can have a very simple singly linked list to implement our stack with. And you can sort of see it right here, right? Like you can just look at this data structure and imagine how we would use this. So we have another variable account that we use to keep track, because counting the things that are in the list requires us to iterate through, and we don't really want to do that because that's an order in in the size of the list function, right? Going back to our analysis of algorithms, it's an order in operation to go in and have to do that. So here's a question: what would be the order of an insert in a linked list in this case in a stack? If we're going to store it at the top, always at the top, what's the order? All right, so the answer to that, I should do one of those little quizzes on the presentation, but the answer to that is it's order 1, right? Because all we have to do is set the next node reference to point to the top and the top to point to the new node that we're adding. And that takes 2 operations. That's a constant. So it's a constant to add. So removing from the stack is the same way. It only takes a constant. So if you think about the array version of the stack, implementation of the stack, think about like what does it take to add things to that stack. So that stack is pretty nice. It's linear. It's order 1 to add, right? For the most part, until we reach a certain point. And then every now and then the add is going to take longer than we expect, because we're going to reach the end of the stack, right? And we're going to have to double the size of the array. And when we do that, we're going to have to copy everything over, right? So what order is that? Would that be copying that over? What order operation would that be? So adding normally would just be order 1, right? Because we just basically set the reference in the array, we increment the top to +1, and we're good to go. That's order 1. But when we have to resize and we have to copy everything over, that's order n. So if we had a really, really large stack, 1 million elements in it, and we wanted to take it to 2 million, that would actually take quite a bit of time. Well, it depends on how fast everything is, but it wouldn't be, it's non-trivial, right? Whereas with a linked list, it doesn't matter how big it is. We never take that hit. We never have to resize. We never have to copy. The other nice thing about the list is if you think about the array implementation, once you double the size of the array, did we ever go back and cut it in half? No, we didn't. It just stayed that size forever, right? But with the linked list implementation, when we remove an element, it's still order 1 to remove, same as the array, but we free up the memory instantly. So we don't waste memory. We don't take that hit in having to resize the arrays. So linked lists for stacks are actually really, really nice things, provided that all we need to do is push things on the top and pull things out. Now, if we want to do more complicated things, which we really shouldn't be doing with a stack anyway, maybe a linked list is not the best. Depends kind of on your use case, right? Sometimes you do have to do those naughty things. All right, so here is our stack, our linked. What are we calling it here? Our linked stack. So we pushed some elements on it, A, B, C, D. So we've pushed A first, B, then C, then D. The count is 4. And this is what it looks like. So we have our linked stack elements up here, which have a link to the next. We have our reference that points to the very first element of the list. And then we have the thing that we're storing inside, which in this case is just a letter, right? So this is our stack implemented using links. It's pretty straightforward to see how it works. So when we put one on, all we have to do, we make the new node, we make the element inside the node point to the E object. Then we set the next pointer to point to top, and then we set top to point to the current thing that we're looking at, right? The current one that we're adding. So it's very easy to add these things onto the stack. Very straightforward. So let's look at some of the code for this. So again, we've got it in this package, JSJF. So we have our public class linear node T. So this is our nodes in our linked list, and you see it has a linear node T next, which is a reference to the next element in the list. And then the T is our generic. That's the type of the object that we're going to store in the list, right? We're going to define that when we instantiate one. So we have private T element. This is the element that we're storing in the list. This is the thing that we're going to store in the list. So this list actually could hold anything. So in our constructor, we're going to set next equal to null. We're going to set element equal to null. Everything's going to be null so that it's all nice and clean. If we are going to call the constructor and pass in an element, we're still going to set next equal to null, and we're going to set the element equal to elem, right? So it's the thing that we're going to store in this particular node. So now we're going to add a function. In the previous instances we were directly using the reference.next, right? But in this, we're going to use the function getNext, which is going to return the reference next. We're going to have another function. So this is our setter. We're going to set the next function for this particular, or the next node for this particular node. We're going to have a function that lets us get the element out. It's going to return the type T. It's going to get the element. It's going to return the element. And remember, this is the thing we're storing inside. And then we're going to have another one that's going to let us set the element so we can set it in case we didn't set it in the constructor, right? If we wanted to, we could, do things like, well, we're always going to do it in the constructor, and we could remove the default constructor. Or make it private, or whatever we wanted to do. All right. So here is our linked stack implementation. So we're going to compose this thing. So here's our linked list class, right? This is our linked list class, our generic linked list class. Here is our generic stack class, which is going to implement the interface for the stack ADT. So the stack ADT, remember, is the interface that defines the accessor functions or the interface functions for the stack abstract data type. The linked stack is going to be an instance of, or it's going to implement that interface, right? So inside of this stack, we're actually going to do the thing that's going to do all the work is going to be our linear node linked list instance. In the last one, it was an array, and this one, it's going to be our linear node linked list. And we're going to have this top reference, and we're going to have this count. So to instantiate this, we're going to make an empty stack, 0 count, null reference for top. We're going to add some elements here. We have to implement the interface, right? So when we implement the interface, we're going to have push, which is going to take an element. Again, this is all generic. It's going to take an element. It's going to make a new linear node for the internal linked list. And it's going to pass in the element in the constructor, and it's going to set next equal to the top. So the current element that we're going to add, which is this temp, we're going to set the next equal to top, and then we're going to make the top equal to the temp. And remember, we do it in that order so we don't accidentally lose reference to the list. And then we're going to increment the count. So what this is going to do is it's just going to add a reference to our list, or it's going to add a node to our list. Okay. We have our pop, which again throws the empty collection exception. So if it's empty, we throw this exception. We're going to say T get result. So this thing is going to return the element on the top, right? It's not going to return the node. It's going to return the element. So we're going to say result. What we're going to return back when someone calls pop is going to be top.getElement. Then we're going to say top equals top points to get points. It's C++. Top equals top.getNext. So we're going to get the next thing here. And the old top now has nothing pointing to it. So it's just going to get deallocated and the garbage collector is going to clean it up. Okay. We're going to decrement the count because we're decrementing this thing, and we're going to return the result. All right. So does that make sense to everybody how that works? Hopefully that's the case. It's, again, just using the linear node class. There's a lot of different ways you could implement this. You could implement this linear node class so that instead of, directly setting next, you just add elements to it, like, add next or something like that, and it actually handles all the pointer or reference manipulation instead of having you do it yourself. So again, implementing the stack using the link, we're going to add a node to the front of the linked list is how we're going to implement our stack. So we're going to do this first, which gets it sets the next to the new node to be the top, and then it sets the top to be the temp. So we basically, if you think about it now, the old top is the next of the new top, right? So hopefully that's pretty straightforward. All right, well, thanks everyone. I hope you enjoyed this chapter on how to use linked lists and how to use them to create stacks. Thanks, and have a good afternoon.